Hi everyone. We saw yesterday in the keynote how important it is to visualize our data, and it's really, really important. I agree with that. But the thing we need to keep in mind is that to generate these very nice graphs, we also need to deal with not so nice programming languages full of curly braces and semicolons, right? So. But we are functional programmers here, and we all know that the solution for that is always the same. We create an embedded EDSL that generates that ugly code for us, right? So let's take an example. Let's think of a semaphore with a very complicated finite state machine that cycles between green and red, right? And after hacking a little bit on Haskell, we can come up with a monadic EDSL for representing this. So we can define a semaphore by creating two nodes with the node combinator, two nodes, one green and one red, and then we can combine them with the rightwards arrow. So we have an edge from green to red and an edge from red to green. That's easy, right? And from there we can generate the ugly code that we are not willing to write. So far so good, but there are two problems with this EDSL, at least two. First one is, when we generate the code, all the semantic information that we have encoded in the names that we use here is not really represented on the generated code. Instead, here we have only sequentially generated names. And the reason for that is that whenever we use do notation in Haskell, the names that we put to the computations doesn't belong to EDSL. They belong to Haskell. And there is no easy way for the programmer of the EDSL to take advantage of these names. And hence, we cannot have them here directly. This is a very common problem for EDSLs generating code. So common that the usual solution for this is that the programmer explicitly asks us to also write the name in the computation that generates the node, write the same name using a string. All right, so this is the common solution. And from here we can generate the code that we originally wanted. But this is, in my opinion, is horrible, right? Because now you have two names for everything for everything in your code, and you need to keep these names in sync. So it's not a nice solution. So a nice solution would be to be able to scrap these names away and still get the generated code reflecting the names that we use in the do notation, right? And there is a second problem here. That is, how difficult it is to report good error messages in embedded EDSLs. So for example, let's say that we want to avoid the user for defining multi-graphs. So a repeated edge, like red to green, should raise an error, right? We can do this very easily as the programmers of EDSL. But at the moment of reporting this error, what is the best thing that we can report? If we don't have any information about the names or the locations, the only thing that we can say is there is a multi-edge somewhere, right? And if we are very reckless, we can also say the internal names that means nothing to the end user. So this is a very common problem. If we have redundant strings, this situation is somewhat better because now we can say the edge red to green has multiple definitions. That's much more useful. If these two definitions are close together, if this definition is in one file and this definition is in another file, good luck finding them, right? So instead, what we would like to get is something like, okay, there is an error in your file in this position. The edge red-green has already been defined in this other file. It's a very concrete error message that we would like to get, and we cannot right now because we don't really know where these things are defined. All right? So these two problems are the ones that we try to solve in this work. All right? And how do we do this? So if you know me, you know that my favorite hammer is to use meta-programming for everything. And it's somewhat possible to achieve this if you know a little bit of template Haskell using quasi-quotas. But the thing is, if you know how to use quasi-quotas, you really want to avoid them because they are horrible to use. And if you don't know them, believe me, your life is much better that way, right? So turns out there is a much more refined tool, and much bigger, by the way, that we can use for solving this problem. That is to use a compiler plugin, all right? So if we take a look at the compiler support in GHC, historically we only had support for core plugins and type checker plugins that are not really useful for us, because what we want is the static information that the user writes that is on the parse stage. So not very lucky so far. But the thing is, since GHC 8.6.1, we also have support for two new kinds of plugins. That is source-to-source plugin and renamer plugins. And the ones that we will use here are source-to-source plugins that let us do exactly what we want. That is to take the freshly parsed AST that contains all the names and all the locations of everything, and we can transform it directly into a new AST. All right? So what is the idea here? The idea is that for every do expression that we find in the code, we will consider separately each one of the statements, and for each one we will create what we call a source annotation. All right? A source annotation is no more than a piece of data of this type, source info, that contains two things. First, it contains a maybe string that represents the fact that a statement could have a name. So, for example, we will have just foo for the first one, and nothing for the second one that doesn't have a bound name. All right? And in the second place, the other thing that we want to keep about each one of these statements is the location in the code where they appear. And this is going to be simply a tuple with a line number, column number, and the file in which is defined. All right? So we can have 42 5 main, 43 5 main, and so on. Right? And now, for a technical reason, this is also going to be a maybe because the compiler might not know in some cases the exact location of something. So don't worry too much about it. All right? But this is the things that we will generate while compiling the code. All right? So if we come back to the semaphore example, we have all the statements, and for each one, we will create a little piece of data that contains all the information that we would like to have in the first place, but it's lost during compilation. So we will have the names for the two nodes, just green and just red, and we will also have all the information about the position where each one of these statements is defined. All right? And now, to bind these two things, to glue the monadic statement with the source annotation, we will use a function, annotate them, that is in charge of exactly that, to glue these two things together. All right? And as you may imagine, defining this function in such a way that it is useful for your DSL and it doesn't break anything while you transform blindly the parse AST is going to be quite difficult. Not so quite, but it's going to be tricky. All right? And all the details are in the paper. I cannot give you much detail about this, but what I can say is that to define this function, we ask for a little bit of help from the part of the programmer of the EDSL. So basically, what we ask the programmer is to tell us how the EDSL should absorb all the source annotations that the plugin generates, right? And for this, there are two options. The first one is to put all the annotations directly in the data they annotate. To do this, it's as simply as extending the annotated type class that we defined. And in the other hand, you can put all the annotations directly in the monad generating the values. that can be done using the annotate M type class. And this one is particularly useful if you have a deep embedding. This one is particularly useful if you have, for example, a state monad that can have for a mapping for annotations and identifiers, stuff like that. All the information and the examples are in the paper, so don't worry too much about this. All right, and now I have a demo to show you. Hopefully. All right, so is that big enough? Right, so what I have implemented here is it's a little proof assistant for propositional logic as a DSL in Haskell, and it has the Coq style of proving by chaining proof tactics. So I will show you a little bit a simple proof. So on the left-hand side, this is my DSL. On the right-hand side, this is the proof state that is generated by my DSL. And every time that I save this file, the proof state is going to be recompiled and re-shown here. All right. So let's take a little look at this. All right. So first here I have two variables, P and Q, that I'm instantiating. And with these two variables, I would like to prove modus ponens. That is, if I have B, if I have P and I have a proof for P implies Q, then I can prove Q. Okay? Hopefully everyone knows about this. So the first thing that we need to check is that as the goal, I have P and P implies Q, right? So this is an implication, and I can introduce the left-hand side of the implication, and this will make me prove Q with the assumption that P and P implies Q holds, and gives me the name H0 for that hypothesis. But I don't really like that name, so I will give an explicit name in the do notation. And now the name is there. All right? So from here, I have an hypothesis that is P and P implies Q, and I can destruct it into two hypotheses, one for P and one for P implies Q, by destructing this hypothesis. All right? And now from here I have two hypotheses, one for P implies Q. And what I can do is to obtain an hypothesis for Q by applying the hypothesis for P to the hypothesis for P implies Q. And with this hypothesis, we can just say, okay, my goal is exactly this hypothesis. Okay? And the thing is proven. All right. But let me put a breakpoint somewhere here. What is important to see is that all the information that I'm showing here is information that is being reified from the EDSL directly. So be the names of the variables P and Q are extracted from the code. The names of the hypotheses that I bind in the do notation are also extracted from the code and shown for the user. And also, every time that I write a tactic, I'm also logging the position where this is happening. So if there is an error, let's say, for example, assumption here, yes, I can say you cannot apply the tactic assumption to the current goal in this position in the code. So you have a very concrete error referring to a place in your EDSL that you can use to find the error. That is very difficult to do without the static information that we are extracting with the plugin. All right? And let's see what happens if we turn off the plugin. Oh, shit. Just a sec. So if we turn off the plugin, all the proof state is not going to be as nice as it could be, right? Because now we have all sorts of sequentially generated names that doesn't really tell me much about what I'm writing, right? So the semantic gap between these two is really big. So we can take it back and everyone is happy. All right. So there is much more in the paper, especially there are a lot of usage examples that you can take a look, so it's easier to adapt the plugin for your EDSL. A lot of discussion about if this is the right way of solving this or not. Hopefully it is. And that's more or less. I would like to see if you have any comments or feedback about it. Thank you very much.